Hello guys, welcome back to lecture series on discrete mathematics, which is based on 2026 a new exam pattern. Okay guys, we have started lecture series based on the set and proposition. Within that mathematical induction I explained in my yesterday's lecture. Now in our today's lecture guys, I'm gonna explain to you all some of the example which based on the mathematical induction. Now see guys, in your in same or end same question paper you will get the question like write down theorem of mathematical induction, or state a theorem of mathematical induction, or you will get the some example for 5 marks like this. We are going to take it in our today's lecture, and you supposed to prove this one is the mathematical induction. Okay, yes. So without further ado, let's get down into our today's lecture. This one example is going to be very important for our lecture. Okay, so maybe similar kind of the example you will get it into your in same or end same exam. Okay, so it is quite easy guys. Okay, so without further ado, let's get down into our today's lecture. I'm going to explain to you all complete details understanding. Okay, now here in our example what we have given, using mathematical induction we have to prove this is some sort of addition of number as a n into n plus 1 by 2 for all or every n small n belongs to natural number n. Okay, yes. Now here we can see guys, okay, it can be easily seen like sum of first n natural number is n into n plus 1 by 2. It is like this. Okay, yes. Now let's continue the solution. We are going for the detailed solution. Okay, sum of first n natural number is n into n plus 1 by 2. Okay, yes. By using mathematical induction we are going to prove it here. Okay, so we have p of n as a statement given 1 plus 2 plus 3 plus n is equal to n into n plus 1 divided by 2. This is our p of n given for all n belongs to natural number n. Okay, and this is our p of n statement given. Okay, this is given. Okay, and what we have to prove, this left hand side and right hand side both are hold using by using mathematical induction. Okay, yes. So by using mathematical induction, by using mathematical induction. Okay, so let's apply mathematical induction. Okay, so what the first step of mathematical induction, it says that we supposed to go for the assumption foundation. Okay, we supposed to go for the foundation. Okay, we are going to prove first of all foundation stage. Okay, so in our foundation stage we consider n which is equal to 1 comma 2 comma 2 up to so on. Okay, and all n smaller than natural number n. Okay, yes, this condition we consider here. Okay, so that means we are replacing value for n is a 1 2 3 and so on in our p of n. Okay, yes. So what is our p of n? Gives us here 1 plus 2 plus n which is equal to n into n plus 1 divided by 2. Okay, so consider n which is equal to 1. We are not going for way bigger value guys. Okay, so bigger values can time taking, smaller value can hold also statements. Okay, so that means we are putting n is equal to 1 in entire statement. Now see that whenever n is 1 in this statement we get only 1. Okay, 1 plus 2 plus n is 1. That means we are going up to the n as a value 1. Okay, so what actually this represents, summation of all n number which n running from 1 to n. Okay, this is the actual representation of this side here. Okay, sum of all number n, but and that n running from 1 to n. So if you're going to replace this summation as in the form of addition, so you will get the 1 plus 2 plus up to n. Okay, so at the initial stage I consider n as a 1. Okay, so n which is equal to 1, that means this one gives only 1. Okay, which is equal to put n as 1 into 1 plus 1 divided by 2. That means 1 which is equal to 2 into 1 2 by 2. this one gives 1 which is equal to 1. Okay, that means whenever we in the foundation step we replace n as a 1, our statement holds. Okay, similarly if you want you can take one more value. Okay, so I'm taking n as a 2. Okay, that means n running from 1 to 2 only. Okay, n running from 1 to 2, that means 1 plus 2, it is remaining only here 1 plus 2 which is equal to n is equal to 2. 2 into 2 plus 1 by 2. 2 into 2 plus 1 by 2. So 1 plus 2 is a 3. 2 into 2 plus 1, 3 to the 6 by 2. So that means we write 3 which is equal to 3, and when you divide 3 as to the both side you get the 1 which is equal to 1 which is equal to 1. Okay, this is our required answer. I hope you all have understood, guys. Foundation step. Okay, foundation means need to replace only the values into our statement. Okay, yes. Now after foundation we are going for assumption. Okay, next step, assumption. In our assumption, what we do, guys, we use n which is equal to k. We assume first n which is equal to k, and in succession we prove n which is equal to k plus 1 hold. Okay, assume p of n holds for n which is equal to k. Okay, what we do, we assume here p of n holds for n which is equal to k. That means we write p of k as, we are writing p of k as, okay, so 1 plus 2 plus n which is equal to k, which is equal to k into k plus 1 divided by 2, and all k which is smaller than natural number. Okay, that we assume. Okay, p of k as, whenever we replace n as a k, that hold. Okay, holds. Okay, so we assume here this statement for left and right hand side hold here. Okay, this is only the assumption. You do not need to prove anything here for the assumption. We just consider n as a k as an initial value for our statement. Okay, now in our succession stage we are going to prove for the k plus 1. Okay, let's move to the next step, succession. In our next stage, succession stage, what we do, we take assumption from p of k and we prove that one hold for p of k plus 1. Okay, so assume here, we assume here, so what do you assume? Assume p of k holds for all k. P of k holds for all k. Okay, that we assume here, and our claim true, for p of k plus 1. Okay, our claim it is true for p of k plus 1. So what is our statement p of n? So the p of m statement we are taking. Okay, 1 plus 2 plus 3 plus n which is equal to n into n plus 1 divided by 2, all n smaller than natural number. Okay, yes, for all n smaller than natural number. This is our given statement. We have to prove this one is hold for p of k plus 1. So instead of n, replace n which is equal to k plus 1. What we are doing, we are replacing n as a k plus 1. So replace wherever you will get the n as a, wherever you will get the n as a k plus 1. Replace everywhere n as a k plus 1. Okay, in our given statement. Okay, so what we get, 1 plus 2 plus 3 plus k plus 1 which is equal to, what I have done, there are infinitely many numbers here in this form of a dot. Okay, so we are not writing that one. So this means plus like this. Okay, yes. So 1 plus 2, I replace n as a k plus 1. Okay, so and n as a k plus 1 here too, k plus 1. So this one is a n as a k plus 1, this n as a k plus 1, and a plus 1 divided by 2. Okay, this one is a replacement of our statement. Okay, yes. So here you can observe, guys, here you can observe our statement is start from 1 plus 2 plus 3 plus up to k plus 1. But what is the before step of a k plus 1? Last step. So k plus 1, whenever you remove 1, you will get the k here. Okay, whenever you remove 1, again k minus 1, again remove 2, k minus 2, k minus 3 up to 1, you will land here. Okay, yes, this is our required statement. Okay, yes. Now by assumption we prove our statement hold for p of k. Okay, and p of k, what it is, says that 1 plus 2 plus 3 plus k, which is equal to k into k plus 1 divided by 2. This one we assume for the p of k. Okay, so 1 plus 2 plus 3 plus k. So replace this assumption over here. Okay, that we assumed before. So what it will be, k into k plus 1 divided by 2. This one is our assumption, plus k plus 1. Okay, this one is the right side, that this one is the side that we assumed before in our assumption. Okay, that I replace 1 to k here. Okay, k plus 1 as it is here. Now k plus 1 into k plus 1 plus 1. Okay, so what we write, k plus 1 and k plus 2 divided by 2. This is our statement. Okay, now our task is that to show left hand side and right hand side both are equal, so that we can conclude easily our succession hold for all the value of a k plus 1. Okay, now it is having denominator 2, so make it denominator 2 here, so that we can take denominator 2 common. Okay, so 2 numerator here, k square plus k plus multiply 2 divide 2. Okay, so that you will get the denominator 2, 2k plus 2 is equal to k plus 1 k plus 2 divided by 2. Okay, so base is 2, then take it once. Whenever we have denominator same, we take it once. Okay, k square, k plus 2k, 3k plus 2 divided by 2, which is equal to k plus 1 k plus 2. Okay, so we want the factorization. Okay, we want the factorization for k square plus 3k plus 2. That means you want the number which is multiplication is a 2 and their addition is a 3. Okay, so we know that 1 and 2, 1 into 2 is a 2, and 1 plus 2 is a 3. Okay, that means we write their factor as a k plus 1 and k plus 2 divided by 2, which is equal to k plus 1 into k plus 2 divided by 2. Okay, okay, this one is our succession stage. Now see that both here LHS and RHS, okay, left hand side and right hand sides are equal. Here left hand side and right hand sides are equal. Whenever left hand side and right hand side are equal, then we say that our assumption for p of k hold, and then p of k plus 1 holds here by assume p of k. Okay, yes. Now we have last step remaining after succession, induction. Okay, which is the conclusion also we call. Last stage induction, or also we called conclusion. Induction also called as the conclusion. Okay, yes. So in our conclusion, what we do, we explain what we have done for the succession. Okay, yes. So statement p of n as 1 plus 2 plus n is equal to n into n plus 1 by 2. Okay, holds for p of k which gives p of k plus 1 is true. Okay, this one is our conclusion. In conclusion, what we do, we conclude what actually we prove into our entire example. Okay, yes, so I hope guys you all have understood this solution. It is very easy solution guys. You just need to remember FASI rule and apply the different values and prove our statement. For mathematical statement sounds mathematically. Okay, yes, now for your reference you can note it down my notes. So here you can see, here from here we have started. Note it down these notes, it will be helpful for your understanding. If you want you can pause the video and note it down. Later on, after assumption we went to this succession here, foundation, assumption, here it is a succession, all the step for succession, and induction at the end we prove here. Okay, I hope guys you all have understood my today's entire lecture. I'm gonna need you all to solve one of the example for your homework and let me know the answer into my comment section. Okay, let's take one example for your homework guys. So here guys, I have added 3 important example which mostly repeated in your previous year question paper. Okay, these are old question but similar kind of the example you will get it in your question paper. Okay, so with the help of mathematical induction we are taking n greater or equal to 1. Prove that 1 into 2, 2 into 3, 3 into 4, their addition should be n into n plus 1 into n plus 2 divided by 3. Many more time repeated question for 5 marks. Okay, again second question, 1 square, 3 square, 5 square, 2n minus 1 square, n into 2n minus 1, 2n plus 1 by 3. Okay, this one is second question. Okay, and third, 1 cubed, 2 cubed, 3 cubed up to n cube, n into n plus 1 by 2 square is equal to 1 plus 2 plus n square. Okay, yes, mostly repeated question guys. Similar kind of the questions you will get it into your coming in sem and end sem question paper. Okay, so make sure that prepare this question properly. Okay, similar kind of the example are having probable chances for your end sem exam. Okay, and in same exam. So I want you all guys to solve this example and comment me answer in my comment section. Okay, this one is compulsory for all my students. Okay, those who are watching my videos, it is compulsory for everyone to comment me answer in my comment section. Okay, that's it for our today's lecture guys. I hope you all have understood and found my today's entire session informatics and helpful for you all. Okay, so that's it for today's lecture. We're going to continue next part into our next lecture. Okay, so thank you everyone, thank you for today's lecture.